This video is about a set of macros I created to create an Excel sheet that processes the data that comes out of this Redi-Rock Geo5 software. Once you get your wall entered into the software, and assuming you have created the 3D version of the wall, which is really, without going to the 3D version, it's really the 2D version of the wall profile. And I've entered ground elevation and then built the wall panels. Once you get to this point, you can export all the panel data here. And I'm not going to do it again, but it ends up as an Excel file that looks like this. I've created a set of macros to take this panel data table and convert it to a drawing profile that can be imported into Excel with all the various blocks that occur at special conditions, such as 90-degree corners. But let me delete this one, we'll do it from scratch. That's the cool thing about this software, you can just tweak it and rerun it. So I would go to my template file and just run the main macro, select my panel data file. And then there's an interface for defining which of the edges are going to be exposed of the wall. You can move the output around on the sheet to some degree. You can switch the parity, the running bond parity, or you can force the first block of the top course to be a half block. And that runs. And produces the new sheet. With basically the profile drawing complete. Now I've built in a set of reinforcing length selections, and all of these are changeable via drop down. So you make the first run and then you can go through and tweak it, or you could go into the code and define the courses. So there are some possibilities there. So it automatically defines edge in the end, 90-degree turns. So this section of the wall is going to be turned back 90 degrees. So it's an outside corner. This is another outside corner with the freestanding wall block selected automatically. Then it's set up to count all the different block types. And accumulate those. It also counts all the specified reinforcing links and counts the occurrences of each length with regard to each reinforcing type. And I've shown here the actual cut length for that specified length. the blocks that are created, or the blocks that are selected, are from this basically is a summary of all the blocks and the conditions where they would apply. Base, top, middle, short block, edge block, etc. Another sheet outlines all the reinforcing types that are available for this run. I've set up optimum cut lengths based on getting the most out of 200-foot rolls. These can be augmented if you wanted to add another length. It'll dynamically add it to the list. You can see here the 19-foot is removed. The panel data is removed or repeated, and I've added 2 columns, the start block and end block column, which is useful. Then we've created a course position array, which is the start block and end block position of each course. And this is numbering the courses top to bottom. And then there's another sheet that has information for each block. There's 499 block in this run. Then in the end, we've created a summary sheet of all the blocks. The GeoGrid table in this summary sheet is not complete until we run the cut optimizer. We can run that from here or from the wall profile here. But if we run it, it'll hit a time limit. And it could run longer if you let it, and it might be a better solution. But ultimately, it's come up with number of rolls, number of cuts of each pattern to optimize the cuts out of the 200-foot rolls, and calculates the number of rolls needed and the number of tubes needed, which is 3 rolls per tube, and the surplus. It turned out we used 8XT and 5XT on this. There were no surplus, but the surplus from the 8XT would be carried to the 5XT here and be used to calculate how many tubes are needed to buy. But once you run the optimizer, the summary sheet is updated with total tubes needed and the block selection needed. So thanks for all the help, Ryland, and getting me up to speed on this. But I obviously got down into a rabbit hole.